We will now use the concepts we developed in rotational motion to solve problems. Well, to do that, you need to be familiar with some of the equations we developed earlier. Is that right? Now, it is easier to write down the formulae for linear motion and then rewrite the corresponding equations for rotational motion. That is much easier. So let's do that to begin with. For linear motion, v equal to v0 plus at is our first equation of motion. How does that translate to rotational motion? Omega equal to omega 0 plus alpha t. X equal to x0 plus v0t plus 1/2 at squared becomes theta equal to theta 0 plus omega 0t plus 1/2 alpha t squared. V squared equal to v0 squared plus 2ax becomes omega squared equal to omega 0 squared plus 2 alpha theta. F equal to ma. What will be the equivalent equation for rotation? Tau equal to I alpha. Work done in linear motion is force multiplied by the distance. Work done in rotational motion is the net torque multiplied by the angular displacement. Kinetic energy in linear motion is 1/2 mv squared. Kinetic energy of rotation is 1/2 I omega squared. Linear momentum P equal to mv. Angular momentum L equal to I omega. Kinetic energy of rolling is 1/2 I omega squared, that is kinetic energy of rotation, plus the kinetic energy of the motion of the center of mass, that is 1/2 mv center of mass. Mostly we will be using these equations. Alright, let's look at the problem. A 3.5 kilogram cylinder of radius 15 centimeter is initially at rest. A rope of negligible mass is wrapped around it and pulled with a force of 17 Newton. Find A, the torque exerted by the rope, B, the angular acceleration of the cylinder, and C, the angular velocity after 5 seconds. In this problem, we have a cylinder and a rope is wrapped around the rim of it, and if I pull on the rope, see what happens? The cylinder rotates. When you pull on the rope, the cylinder rotates. Now tell me, what is the torque? The axis of rotation is through the center. This is the axis of rotation. Therefore, the torque arm is the perpendicular distance between the axis and the force, that is the string. That means the torque arm is the radius of the disc. Is that right? Because this is the force where I'm pulling, and the force, the distance of this force from the axis is the radius. Therefore, the torque will be the force multiplied by the radius. Well, that concept must be clear. Okay, let's go back and do the problem now. Well, this is our cylinder and the rope is wrapped around it, and we pull the rope by a certain force. The radius of the cylinder is 0.15 meter. The force that you apply on the rope is 17 Newton. So, mass of the cylinder is 3.5 kilogram. Its radius is 0.15 meter. and the force applied on the string is 17 Newton. F equal to 17 newtons is at right angles to, as I showed you, this is the radius, and that F equal to 17 Newton is at right angles to this radius. Therefore, the torque produced by that force is R times F sine theta. Remember, sine theta is 90 degrees, therefore sine theta is 1. Theta is 90 degrees, therefore sine theta is 1. So torque equal to R times F, that is 0.15 times 17 is 2.55 meter Newton. What do you want to find in the B part? We want to find the angular acceleration. Now, what is the equation that connects the angular acceleration to the torque? You see, in linear motion, F equal to ma. In rotational motion, tau equal to I alpha. So, if you can now find the moment of inertia of the disk, we know tau, therefore we can find the angular acceleration. Alright, let's now find the moment of inertia of the disk. A cylinder is the same as the disk of radius r. What is the equation for the moment of inertia of a disk? I equal to 1/2 mr squared. Is that right? Now that will be 0.5, that is 1/2. Mass of the disk is 3.5 kilogram and the radius is 0.15. So 1/2 mr squared is 0.04 kilogram meter squared. And now tau equal to I alpha, therefore alpha equal to tau divided by I, and we have those values. Tau is 2.55 meter Newton and I is 0.04 kilogram meter squared. Therefore, the angular acceleration is 63.75 radian per second squared. You can see how simple these become once you approach them systematically like this. What is the next question we need to answer? Find the angular velocity of the cylinder after 5 seconds. Well, you know the angular acceleration and you know the initial angular velocity. What is the initial angular velocity? The disk is initially at rest. So the initial angular velocity is 0. The angular acceleration we know and the time we know. Therefore, we can now say omega equal to omega 0 plus alpha t. Is that right? Alright. Omega 0 is 0, t equal to 5 seconds. Omega f equal to omega 0 plus alpha t. And that will be 0 plus alpha we calculated, 63.75 radian per second squared, times 5. That is 318.75 radian per second. And that is the angular velocity of the disk after 5 seconds. Alright, let's try another problem. A wheel mounted on an axle that is not frictionless is initially at rest, omega 0 equal to 0. A constant external torque of 50 Newton is applied to the wheel for 20 seconds, giving it an angular velocity of 600 rpm. The external torque is then removed and the wheel comes to rest in 120 seconds. A. Find the moment of inertia of the wheel, and B. the frictional torque that brings the wheel to a stop. Now, you apply external torque and the wheel rotates. When the external torque is removed, the wheel comes to a stop. Why? because of the torque applied by the friction, and we need to find that torque. Alright, well, disregard this. I just put in a wheel there that is rotating. Now what are the data we have? Omega 0 equal to 0. Omega F is given to be 600 revolutions per minute. Convert that to radian per second. Multiply by 2 pi and divide by 60. So omega F is 20 pi radian per second. Tau equal to 50 meter Newton. Well, the external torque applied is 50 meter Newton and the time is 20 seconds. So when an external torque of 50 Newton applied for 20 seconds gives it this angular velocity. Well, we first find the angular acceleration. Tell me, what will be the equation we will use to find the angular velocity? Well, we can find the angular velocity by knowing the initial angular velocity. We need to find the angular acceleration. We know the initial angular velocity, the final angular velocity, and the time, and that's enough for us to find the angular acceleration. So omega F equal to omega 0 plus alpha t, or alpha equal to omega F minus omega 0 divided by t. That will be omega F minus omega 0 is 20 pi radian per second divided by 20 seconds. That is pi radian per second squared. That is the angular acceleration. What are we looking for in part A? Find the moment of inertia of the wheel. Can you tell me how we can obtain the moment of inertia if you know the angular acceleration and we know the torque that produces that angular acceleration? What is the relation between the torque and the angular acceleration? Tau equal to I alpha. Well, tau equal to I alpha, we can now find I, the moment of inertia. So I equal to tau divided by alpha, that is 50 meter Newton divided by pi radian per second squared, and that is 50 divided by pi kilogram meter per second squared. We can leave it like this as an exact answer. So we now have the moment of inertia of the wheel. In the next part, the external torque is now removed and the wheel is now going to come to a stop under the action of the frictional torque. Alright. Now, when the external torque is removed, the frictional torque, let's call it tau F, produces a negative angular acceleration, bringing the wheel to a stop. And we have omega 0 in the beginning, that is the moment when the external torque is removed, the wheel is rotating with this angular velocity. And its angular velocity is going to come to 0. So omega 0 is 20 pi radian per second. Omega F equal to 0. And the wheel come to a stop in 120 seconds. And we also know that the moment of inertia of the wheel is 50 divided by pi kilogram meter per second squared. Alright, what do we do first? We have enough information here to find that acceleration produced by the frictional torque. So let's do that. We first find the acceleration caused by that net torque applied by the friction. And how do we do that? Omega F equal to omega 0 plus alpha t. We know omega F, we know omega 0, we know t, therefore we solve for alpha, and using the values omega F equal to 0, Omega 0 is 20 pi radian per second divided by 120 seconds. That is negative pi over 6 radian per second squared. So the frictional torque produces a negative acceleration of negative pi by 6 radian per second squared. Well, we know the acceleration caused by the frictional torque. We know the moment of inertia of the wheel. Can you use these two quantities to figure out the frictional torque? Tau F equal to I alpha. I is 50 divided by pi kilogram meter squared times alpha is negative pi over 6 radian per second squared. And you see the advantage of leaving the answer in the exact form. You can see the pi and pi will now cancel. That is negative 25 over 3 meter Newton is the frictional torque. Alright, that's a good problem, and I want you to learn how to do problems like this. Okay, another one. A light meter stick is loaded with masses of 2 kilogram and 4 kilogram at the 30 centimeter and 75 centimeter positions respectively. What is the moment of inertia about an axis through the 0 centimeter end of the meter stick? What is the moment of inertia about an axis through the center of mass of the system? Use the parallel axis theorem to find the moment of inertia about the axis through the 0 centimeter of the stick and compare the result with the results you have in part A. Well, moment of inertia of an object of mass m situated at a distance r from the axis of rotation. Do you remember that equation? What is the moment of inertia of an object of mass m placed at a distance r from the axis of rotation? It is mr squared. The moment of inertia of an object placed at a distance r from the axis of rotation is mr squared. So we can now, in part A, we want to find the moment of inertia about an axis through the 0 centimeter. That means about an axis passing through the 0 centimeter of the meter stick. Alright, the moment of inertia of a mass m situated at a distance r from the axis of rotation is given by I equal to mr squared. So we can now find the moment of inertia of these two masses about an axis that passes through the 0 centimeter mark using this relation. For the axis passing through 0, m1 is at a distance r1 from the axis of rotation, and m2 is at a distance r2 from the axis of rotation, where r1 equal to 30 centimeter and r2 equal to 75 centimeter. Okay, let's look at that again. Now, what is the moment of inertia of object 1 about this axis? We are looking for the moment of inertia of these two objects about an axis that passes through the 0 centimeter mark. So, moment of inertia of m1 about the axis that passes through 0 will be m1 r1 squared. Moment of inertia of m2 about the same axis will be m2 r2 squared. The total moment of inertia will be m1 r1 squared plus m2 r2 squared. And we know those values. M1 is 2 kilogram, R1 is 0.3 meter, M2 is 4 kilogram, R2 is 0.75 meter, and that gives us 2.43 kilogram meter squared is the moment of inertia of these two objects about an axis passing through the 0 centimeter mark. Okay. First of all, we need to find the moment of inertia of these two objects about an axis that passes through the center of mass. Well, in order to do that, we need to know where the center of mass is. Where is the center of mass? X center of mass is m1 x1 plus m2 x2 divided by m1 plus m2. Now, m1 is 2 kilogram, x1 is 0.3 meter, plus m2 x2 is 4 meter times 0.75 meter divided by m1 plus m2, and that is 0.6 meter. So the center of mass is 0.6 meter. We now need to find the moment of inertia of these two objects about this axis that passes through the center of mass. Well, the moment of inertia of m1 about that axis will be m1 times the square of this distance. Is that right? Okay, let's put that down. The distance of m1 from the center of mass is r1 equal to 0.6 minus 0.3. This distance is r1, and that r1 is, up to here it is 0.6. 0.6 minus 0.3, that is 0.3 meter. The distance of m2 from the center of mass is, what is that distance? The distance of m2 from the center of mass is this distance, r2. And what is that equal to? 0.75, 75 centimeter. 0.75 minus 0.6, that is 0.15 meter. Alright, the total moment of inertia about the axis that passes through the center of mass is m1 r1 squared plus m2 r2 squared. And we know those values: 2 times 0.3 squared plus 4 times 0.5 squared. That is 0.27 kilogram meter squared. That is the moment of inertia of these two objects about an axis passing through their center of mass. Okay, now the third part is use the parallel axis theorem to find the moment of inertia about the axis passing through the 0 centimeter mark and compare the result with the result in part A. Now, we need to find the moment of inertia of these two objects about an axis that passes through the center of mass using the parallel axis theorem. Now, according to the parallel axis theorem, I0, well, I0 stands for the moment of inertia of these two objects about an axis through the 0 centimeter mark. I0 equal to I center of mass plus mh squared, where h is the distance of this axis from the axis that passes through the center of mass. And tell me, what is that distance here? What is the distance between an axis that passes through the 0 centimeter mark and the axis that passes through the center of mass? That h equal to 0.6. And what does this m stand for? M is the total mass of the system, which is 2 kilogram plus 4 kilogram, that is 6 kilogram, isn't it? So the total mass of the system is 6 kilogram, and the distance of the axis that passes through the 0 centimeter from the axis that passes through the center of mass is 0.6. So M is 6 kilogram, H is 0.6, and therefore we have I0 equal to I center of mass. We just calculated the moment of inertia of these two masses about an axis that passes through the center of mass, and we got that as 0.27 kilogram meter squared. So I0 equal to 0.27 kilogram meter squared plus 6 kilogram times 0.6 meter squared, that is 2.43 kilogram meter squared. Do you remember this value? This is exactly the same result we obtained in part A. Is that right? So, using parallel axis theorem, we get the same result we calculated in part A. We calculated in part A the moment of inertia about an axis that passes through the 0 mark as m1 r1 squared plus m2 r2 squared, and we got the same result. Okay, another problem. Two masses are suspended from a pulley as shown on the right. The pulley has a mass of 0.2 kilogram and a radius of 0.15 meter and a constant torque 0.35 Newton due to friction between the rotating pulley and the axle. So there is a constant frictional torque. 0.35 meter Newton is the frictional torque between the pulley and the axis of rotation. Means that will be opposing the rotation caused by an external torque. Well, if M1 equal to 0.4 kilogram and M2 equal to 0.8 kilogram, what is the magnitude of their acceleration? If you remember, we talked about the motion of connected masses earlier on, about 2 or 3 lessons ago. Now, we will use the same concept here. The only difference here is that now the friction between the pulley and the axis of rotation is taken into consideration. Earlier, we did not consider that. So, what we're going to do is, we are going to isolate each object. We will look at the net force acting on M1. We will look at the net forces acting on M2 and use the law of motion. F net equal to MA for M1 and M2, because the motion of M1 and M2 are both linear. So we can use F net equal to MA for these. But when it comes to the pulley has a rotational motion. Now, what is the net torque on the pulley? There will be a torque, an external torque, and then there is a frictional torque. The net torque will be the external torque minus the frictional torque. And what is net torque equal to? The net torque equal to I alpha. So we are going to produce 3 equations. One equation for the motion of the mass M1, a second equation for the motion of mass M2, and a third equation for the rotational motion of the pulley. Alright, let's do that. Since the pulley offers friction, the tension on the string on the right and on the left will not be the same. You see, in a previous case, when we did a problem like this, we said the tensions on each part of the string is the same because they represent the same string, and the pulley at that time was frictionless. Since there is friction between this pulley and its axis of rotation, the tension on the string on the right is not the same as the tension of the string on the left. So let T1 be the tension of the string on the right. So this is T1. The tension on the string on the right is T1. And let T2 be the tension on the string on the right. Okay. Now, in which direction you think the system will be moving? Let's identify the forces acting on M1. Since M2 is a bigger mass, we would assume that the system is going to move like this. M1 is going to move up and M2 is going to move down. So, let's identify the forces acting on M1. Tell me, what are the forces acting on M1? Of course, the weight of M1 will be acting vertically down, and the tension T1 is acting vertically up. Let's first of all find the weight. The weight of M1 is M1G. Its mass is 0.4 kilogram. Multiply that with G, you get 3.92 Newton, and that is acting vertically down. 3.92 Newton is acting vertically down on M1, and T1 is acting vertically up. So the tension T1 acts vertically up. Assuming that M1 moves up, that's what we had started with. Because M2 is greater, we would assume that M2 will move down and M1 will move up. We have the net force on M1 is T1 minus 3.92. Now remember, we are only considering the magnitudes here. So T1 minus 3.92 is the net force on M1. Now, if F net is the net force on M1, we would say F net equal to MA. Is that right? F net equal to MA, or T1 minus 3.92 Newton equal to M1A. M1 is 0.4 kilogram times A. Now we have an equation that contains two unknowns, T1 and A. We can obtain a similar equation by taking the motion of M2. Well, I'm sure you can do this now on your own. What are the forces acting on M2? Its weight will be M2G, 0.8 kilogram times 9.8 meters squared. That is 7.84 Newton acting vertically down. So the weight of mg is 7.84 acting vertically down. What is the tension on the string? The tension on the string, we said earlier, that is T2. T2 acts vertically up. There you are. So what is the net force on the mass M2? Since the mass M2 is moving down, we would say the magnitude of the net force is 7.84 Newton minus T2. So this is the net force, 7.84 Newton minus T2. And this net force produces an acceleration on M2 such that net force F net equal to MA. The net force equal to M2 times A. 7.84 Newton minus T2 equal to 0.8 A. Now, do you agree with me that acceleration of these two, both the masses are the same? Yes, they are. They cannot be different because they are connected. If one is accelerating, the other also has the same acceleration. So, we have now a second equation, 7.84 Newton minus T2 equal to 0.8A, and the variables here are A and T2. the first equation, we have the variables a and t1. So we have two equations and three unknowns, t1, t2 and a. We cannot solve these equations. We need to get a third equation. Where is the third equation going to come from? It's going to come from the rotation of the pulley. Alright, can you tell me, what is the net torque that rotates the pulley? The net torque. When you consider the rotation of the pulley, you must understand this T2 will be pulling this pulley on the side. T2 will be pulling it down here, and T1 will be pulling it down on the other side. Therefore, the net external force applying a torque will be T2 minus T1. And that external force multiplied the radius of the disc will give you the net external torque. Okay. Now, let's consider the forces acting on the pulley. T1 tends to rotate the pulley clockwise. Do you understand that? This T1 will be trying to rotate the pulley clockwise, whereas T2 will be rotating the pulley in the counterclockwise direction. There you are. T1 rotates the pulley in the clockwise direction, and T2 will then rotate the pulley in the counterclockwise direction. The net force on the pulley, therefore, is T2 minus T1. And the net force will be acting down here. And what is the distance of that force from the axis of rotation? It is the radius of the pulley. Therefore, the external torque will be the net external force multiplied by that radius. This net force produces an external torque on the pulley given by tau external is T2 minus T1 times the radius of the pulley. This is the external torque. Now here, R is the radius of the pulley, which is 0.15 meter. Therefore, I can now say tau external is 0.15 times T2 minus T1. And the frictional torque, tau friction, we know that. Tau friction is 0.35 meter Newton, will oppose the external torque. So if the external torque is trying to rotate the pulley in the counterclockwise direction, the frictional torque will be acting in the opposite direction. What is therefore the net torque on the pulley? The net torque, tau net, is external torque minus the frictional torque, because the frictional torque always opposes motion. That is, now this is the external torque in the counterclockwise direction, and this is the frictional torque in the opposite direction. The net torque will be the external torque minus the frictional torque. Alright, tell me what did we get as the external torque? Is T2 minus T1 times 0.15. So T2 minus T1 times 0.15 is the external torque, minus the frictional torque is 0.35. So this is the net torque on the pulley. And now you tell me, what does the net torque do on the pulley? The net torque will produce an angular acceleration on the pulley, given by the equation tau net equal to I alpha. Since the angular acceleration alpha of the pulley is caused by this net torque, we can say this tau net equal to I alpha. This net torque will be equal to I alpha. So I can now take this quantity. Well, do we know I? I is the moment of inertia of the pulley, and the pulley is the disc. What is the moment of inertia of a disc? Is 1/2 mr². Do we know these values? I equal to 1/2 mr². We know the mass, we know the radius, therefore you have mass is 0.2 kilogram, the radius is 0.15 meter, so the moment of inertia of the disc is 0.00225 kilogram meter square. So we have tau net is this quantity, I we know, and alpha is the angular acceleration. And you know that A equal to R alpha, isn't it? A point on the disk will have a tangential acceleration A, which is equal to R times the angular acceleration. Therefore, we can now find alpha in terms of A. So what we're going to do is, we are going to eliminate alpha and write that in terms of A. So alpha equal to A over R, and that will be A over 0.15. And that will be A over 0.15 is 6.75 A. I want you to watch how I replace this alpha in terms of A, the linear acceleration. Why is it necessary? Because the two equations we have developed so far are equations that contain T1, T2 and A. Now, we cannot have a third equation that contains yet another variable alpha. We need to express that alpha in terms of A. And that's what I'm doing here. So how did I do that? I know that A, the linear acceleration, equal to radius times the angular acceleration. Therefore, alpha equal to A over R. That will be A over, the radius is 0.15 meter. That is 6.7 A. And look at this. I have the value of I is 0.00225 kilogram meter squared, and alpha equal to 6.7 A. Therefore, what is net torque? Equal to I alpha, I is 0.00225 kilogram meter squared, and alpha equal to 6.7 A, and that is 0.015 A. So tau net is 0.015 A, and therefore this quantity can be equated to this quantity, which is tau net. Okay? So we will now take this quantity and equate it to 0.015 A to produce a third equation on T1, T2 and A. Let's do that. So we will now have 0.015 A equal to 0.15 times T2 minus T1 minus 0.35. Let's simplify that equation. Rearranging this will give me this. Now distribute 0.15 and rearrange it. It will become 0.15 T1 minus 0.15 T2 plus 0.015 A equal to negative 0.35. You have now three equations and three variables, and you know how to make a matrix, how to make matrices and solve them. Rearrange those three equations. Look at the way I'm writing them. T1 plus 0 T2 minus 0.4 A equal to 3.92. That is our first equation, this equation. And the second equation is 0 T1 plus T2 plus 0.8 A is 7.84, rearranging this equation. We are aligning T1, T2 and A on the left side and writing the constant numbers on the right side. And now you have equations 1, 2 and 3. Okay, I want you to make a matrix using these coefficients. It will be a 3 by 3 matrix. So you make a matrix A, and the matrix B will contain these constant numbers, and A inverse multiplied by B will give you these values. T1 equal to 4.2 Newton, T2 equal to 7.3 Newton, and A equal to 0.72 meter per second squared. A very important type of problem, and I'm sure you have followed the basic logic for solving this problem. Alright, try this on your own, and that will be a very good practice for you. Another one. A unit is 10 centimeter and mass 5 kilogram is rolling without slipping. Now, one of the things you must consider when a disk is rolling without slipping, its center of mass will be moving with a velocity v center of mass, which will be equal to r omega, r times the angular velocity. That is very important. With an angular velocity of 15 radian per second, a smooth inclined plane is in its path. Find the height to which the ball will climb on the incline. We have a sphere, not a disk this time. Now, do you remember the expression for the moment of inertia of a sphere about an axis through its center of mass? I center of mass is 2/5 m². Alright, so here is our sphere, which has a mass of 5 kilogram, a radius 0.1 meter, and it is rolling with an angular velocity of 15 radian per second. What is the kinetic energy of a rolling object? The kinetic energy of a rolling object is the kinetic energy of rotation, which is 1/2 I omega squared, plus the kinetic energy of the linear motion of the center of mass, 1/2 mv center of mass squared. The moment of inertia of the sphere, let's find the moment of inertia first, is 2/5 m² We know the mass, we know the radius, so use those values, 2/5 m², and that will be 0.02 kilogram meter squared is the moment of inertia. K translational. The disk is rolling, means it has a rotational motion and a translational motion. What is the kinetic energy of the translational motion of the disk? Not the disk, sphere. K translational is 1/2 mv center of mass squared. Well, and v center of mass is r omega. Is that right? That's right. So that will be 1/2 m times, I replace this v center of mass by r omega. And that will be 1/2 times m is 5 kilogram, r is 1.1 meter, and omega is 15 radian per second. So this quantity is the angular velocity, 0.1. This quantity is radius multiplied by the angular velocity, and that is your v center of mass, and so we square it. Okay, so 1/2 times 5 kilogram times the quantity 0.1 times 15, and then square it, and that gives you 5.6 joules is the kinetic energy of translation. What is the kinetic energy of rotation? 1/2 I omega squared. And we know the value of I, we know the value of omega, So that will be 1/2 I times omega squared. That is 2.25 joules. So when this sphere comes at the bottom of that inclined plane, it has a total kinetic energy of 5.6 plus 2.25. That is the total amount of energy here. How much is that? It's 7.85 joules. 5.6 joules plus 2.25 joules is 7.85 joules is the total kinetic energy of the sphere when it comes to the bottom of the inclined plane. It is now going to roll up so that all the kinetic energy is now going to become potential energy. Alright, so Ki, initial kinetic energy, is 7.85 joules. The total energy of the rolling sphere when it is at the bottom is 7.85 joules. Its potential energy there will be 0. So now all this energy is going to be converted to potential energy when it rolls to a height h. There it rolled to a height h. This is h. What is the potential energy there? The potential energy of the object placed at a height h is mgh. Mass is 2 kilogram, g is 9.8, and h we don't know, we need to calculate it. Now, the total initial energy must be equal to the final total energy. Is that right? So we say 7.85 joules, which is the total energy when it came to the bottom of the inclined plane. All that energy is now used in gaining potential energy. So 7.85 joules equal to 19.6 H. Therefore, H equal to 7.85 divided by 19.6. That is 0.4 meter. Okay. Another one. A flywheel with a moment of inertia 4.5 times 10 to the power of 2 kilogram meter squared rotates with a speed of 7,500 RPM. How much work is required to bring it to rest? Well, if you know the concept of kinetic energy is a measure of the work done to give the wheel an angular velocity. And now it has this angular velocity. What is the amount of work that you need to bring it to rest? It is the opposite of the amount of work done to give it that kinetic energy. Alright? So how much work is required to bring it to rest? If this is done uniformly in 1.5 minutes, how much power is expended? It's a very simple problem. It's a two-step problem. First of all, the moment of inertia of a wheel, we will assume that the wheel, well, it is given to us. The moment of inertia is given to us. I equal to 4.5 times 10 to the power of 2 kilogram meter squared. The initial angular velocity, omega I, is 7,500 RPM. Convert that to radian per second. So multiply by 2 pi, divide by 60. So omega I is 250 pi radian per second. You know the moment of inertia, you know its kinetic energy of rotation. You know the angular velocity of rotation. Tell me, what is the kinetic energy of rotation? The initial kinetic energy of rotation is Ki is 1/2 I omega I squared. 1/2 I omega I squared. We know I, the moment of inertia. we know omega I, that is 250 pi, and that will be 1/2 times 4.5 times 10 to the power of 2 times 250 pi all squared. And that gives 1.39 times 10 to the 8 joules. Now, this is the amount of kinetic energy the wheel now has. What is the amount of work you need to do to bring it to rest? It is the opposite of this quantity. Now, this is a measure of the work that needs to be done to bring the flywheel to rest, but in the opposite direction. So the work required is negative 1.39 times 10 to the 8 joules. Again, one more time. Kinetic energy is a measure of the work done to give an object an angular velocity, or if the object is already rotating, its kinetic energy is a measure of the work that needs to be done to bring it to rest. So if it has this much kinetic energy, then the work that needs to be done to bring it to rest is negative of that quantity. Alright, if this work is done in 1.5 minutes, how much power is expended? Power is rate at which the work is being done. Power is work done divided by the time. 1.39 times 10 to the 8 joules of work is done in 15 minutes. 15 times 60 seconds. That is 1.5 times 10 to the 6 watt is the power developed or the power expended. Okay, let's do another one. A uniform disk of radius 0.12 meter and mass 5 kilogram is pivoted such that it rotates freely about its axis. A string wrapped around the disk is pulled with a force of 20 Newton. What is the torque exerted on the disk? What is the angular acceleration of the disk? If the disk starts from rest, what is the angular velocity after 3 seconds? What is the kinetic energy after 3 seconds? What is the angular momentum after 3 seconds? Find the total angle the disk turns in that 3 seconds. And finally, show that the work done by the torque equal to its kinetic energy. All these are one-step problems actually. Just use the principles we discussed so far. So none of these is involved more than a single step. Okay, let's go. First of all, we have a disk of radius 0.1 meter and mass 5.1 kilogram pivoted so that it can rotate about a horizontal axis. Alright. Now, we got the mass of the disk is 0.5 kilogram. The radius of the disk is 0.12 meter. A tangential force of F equal to 20 Newton is applied on the disk. This is the first thing. What is the torque exerted on the... Well, I just showed it to you earlier that if you have a disk like this and if you apply a tangential force, the torque of that tangential force will be, what will be the torque? It will be the force multiplied by the radius of the disk. Alright, so as I said, it's a single step problem. Now, F equal to 20 Newton is tangential to the disk, that is perpendicular to the radius. Therefore, torque tau equal to radius multiplied by that force, and that will be 0.12 meter times 20 Newton that is 2.4 meter Newton, is the torque produced by that force. Well, once you know the torque, you can find the angular acceleration. Well, in order to do the angular acceleration, we need another quantity. What is that? We need the moment of inertia. Alright, the moment of inertia of a disk is 1/2 mr². So that will be 1/2 times 5 kilogram. I wrote m equal to 0.5 kilogram. Yeah, it has to be 5 kilogram. So that will be 1/2 times 5 kilogram times r², 0.12 squared. That is 0.036 kilogram meter squared. So we now know the torque, 2.4 meter Newton. We know the moment of inertia. Therefore, we can find the angular acceleration of the disk. Tau equal to I alpha. Therefore, alpha equal to tau over I. That will be 2.4 meter Newton divided by 0.036 kilogram meter squared. That is 66.7 radian per second squared. Okay, so we have done part B. What's part C? If the disk starts from rest, what does that mean? Omega 0 equal to 0. What is the angular velocity after 3 seconds? Well, simple use of the formula. Omega f equal to omega 0 plus alpha t. Where we have this alpha, we will carry this alpha value with us. So omega 0 we know is 0. Alpha we just calculated. Time is 3 seconds. We need to find omega f. Omega f equal to omega 0 plus alpha t. That will be 66.7 radian per second squared times 3 seconds. That is 200 radian per second. Alright, now what is D? We need to find the kinetic energy. What is the kinetic energy? Kinetic energy of rotation is 1/2 I omega f squared. Well, we know I, we just calculated I earlier. We know omega f we just calculated. Therefore, kinetic energy of rotation is 1/2 times I is 0.036 kilogram meter squared times omega squared is 200 radian per second squared, and that is 720 joules is the kinetic energy after 3 seconds. What is E? Angular momentum. What is the angular momentum at that time? Angular momentum equal to I omega. Again, we know I, 0.036 kilogram meter squared. We know omega. We have the omega value. Therefore, angular momentum is 0.036 kilogram meter squared times 200 radian per second. That is 7.2 kilogram meter squared per second. Now, what is the total angular displacement during this time, during this 3 seconds? We know that the theta 0 is 0, we say starting from 0. Omega 0 is 0, is that right, starting from rest. Alpha is 66.7 radian per second squared. T equal to 3 seconds. We need to find theta, the angular displacement. Which of the equations will you use? Theta equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. There you are. Where theta 0 is 0, omega 0 is 0, so the first two terms will go. That will be 1/2 alpha, 66.7 radian per second squared, times t squared, 3 seconds all squared. And that is 300 radian is the angle it described during that time. Suppose I ask you, how many revolutions did it complete during that time? How do you do that? 300 radians is how many revolutions? Each revolution is 2 pi radians. Therefore, 300 radian will be 300 divided by 2 pi revolutions. All right, what's the next thing that we need to find? In G, we need to find the work done. The work done in rotation is tau times the angular displacement. Tau theta. Tau we know is 2.4 meter Newton. Theta we just calculated 300 radians. Therefore, work done, rotational work done, is tau times theta, 2.4 meter Newton times 300 radian. That is 720 joules. Do you remember the kinetic energy we calculated? What is the kinetic energy amount we calculated? 1/2 I omega squared is 720 joules. Look at this. Kinetic energy is a measure of the work done to give the object a particular angular velocity. So the work done is a measure of its kinetic energy. Suppose I ask you, what is the amount of work that now needs to be done to bring this disk to stop? The amount of work that needs to be done to bring it to a stop will be negative 720 joules. All right? Okay. Another problem. What is the angular momentum of a 2-gram particle moving in a horizontal circle of radius 15 centimeter with an angular speed of 6 pi radian per second? Angular momentum is mv times r. Well, we have the mass as 2 times 10 to the negative 3 kilogram, 2 gram. R, the radius is 0.15 meter and omega is 6 pi radian per second. I equal to mr squared, is that right? The moment of inertia of a particle of mass m at a distance r from the axis of rotation is I equal to mr squared. So in this case, the mass is 2 kilogram, the radius of the disk is 0.15 meter, and therefore the moment of inertia of this particle about the axis of rotation is 4.5 times 10 to the negative 5 kilogram meter squared. Well, if you know the moment of inertia and the angular velocity, can you calculate the angular momentum? L equal to I omega. And we just calculated I, we know omega, therefore angular momentum is 4.5 times 10 to the negative 5 kilogram meter squared times 6 pi radian per second. And that is 8.5 times 10 to the negative 4 kilogram meter squared per second. Let's do one more problem. A skater has a moment of inertia 100 kilogram meter squared when his arms are outstretched, and a moment of inertia of 75 kilogram meter squared when his arms are stuck close to his chest. If he starts to spin at an angular speed of 2 revolutions per second with his arms outstretched, what will his angular speed be when they are tucked in? You can see this is a question using the conservation of angular momentum. Is that right? I1 omega 1 equal to I2 omega 2. Alright, I1 is 100 kilogram per meter squared and I2 equal to 75 kilogram meter squared. I1 is the moment of inertia when his arms are outstretched. I2 is the moment of inertia when the arms are tucked in. Now, what is the angular velocity? What is the angular velocity initially when the arms are outstretched? It is 2 revolutions per second. You can leave it in that unit. If you leave omega 1 in revolutions per second, omega 2 will also be in revolutions per second. Or you can convert it as radian per second. 2 times 2 pi radian per second. Is that right? Revolutions per second is multiplied by 2 pi to make it radian per second. Since the angular momentum is conserved, we have I1 omega 1 equal to I2 omega 2. And therefore omega 2 equal to I1 omega 1 divided by I2. And that will be I1 we know, omega 1 we know, and I2 we know. And that will be 16.8 radian per second will be, and that's the reason why the skater will now go faster. It's almost, is that right, much bigger than the earlier angular velocity. Well, we have now done a spectrum of different types of problems, and you must be able to do now any basic 1 or 2 step problems using the concepts of rotation. Alright, I'm going to stop this lesson here. I will take you to the next lesson, which is conditions of equilibrium of an object under the action of different forces. I will see you for that lesson later on.